You are listening to Node.js for everyone, building modern applications from scratch. Subscribe to keep up to date on our latest audiobooks. Node.js for everyone, building modern applications from scratch. Chapter 1, The Node.js Revolution. What, why, and when? Imagine a popular coffee shop, bustling with customers all ordering their favorite lattes, espressos, and pastries. In a traditional setup, if the barista could only prepare one drink at a time and had to wait for it to be completely finished before even taking the next order, the line would stretch out the door and never move. Customers would grumble, and many would simply leave. This, in essence, is what blocking operations look like in the world of computer programs. When one task must finish entirely before the next can even begin, it creates bottlenecks. Now imagine a different coffee shop. The barista takes multiple orders, writes them down, and then starts preparing drinks in parallel. While the espresso machine is brewing coffee for one order, the barista might be steaming milk for another and grabbing a pastry for a third. As soon as a drink is ready, they hand it over and move on to the next one that's ready, or pick up a newly completed order. The line moves swiftly, and customers are happy. This is closer to how Node.js operates, employing what's called non-blocking or asynchronous operations. It allows multiple tasks to be in progress simultaneously, maximizing efficiency. The problem Node.js solved. For years, JavaScript was primarily confined to the web browser. It powered interactive elements on websites, animations, form validations, dynamic content updates, but it couldn't run outside the browser environment. If you wanted to build the backend of a website, the part that handles user accounts, stores data in a database, or sends emails, you typically had to use languages like PHP, Python, Ruby, or Java. This meant developers often had to switch between different languages and mindsets for the front-end and back-end, adding complexity and time to development. In 2009, a visionary developer named Ryan Dahl saw a significant inefficiency in traditional web servers when handling many simultaneous connections. These servers often waited idly for input-output, I/O, operations to complete things like reading from a database, fetching data from another server, or writing to a file. During these waits, the server process would be blocked, unable to do anything else for other users. This was like our first coffee shop barista, standing by idly while the espresso machine brewed. They were unproductive during waiting periods. Dahl proposed a radical solution. What if JavaScript, with its inherent event-driven and non-blocking nature, how it naturally responds to user clicks and network requests in the browser, could be lifted out of the browser and used for server-side operations? And what if it could handle I/O operations in a non-blocking way, allowing it to serve thousands of users concurrently with a single process? This audacious idea laid the foundation for Node.js. What exactly is Node.js? Node.js isn't a programming language, nor is it a web framework like some might assume. Instead, it's a runtime environment. Think of it as a special engine that takes your JavaScript code and executes it directly on your computer's operating system, rather than demanding it be run within the confines of a web browser. At its core, Node.js is built on Google Chrome's V8 JavaScript engine. This is the exact same powerful engine that powers the Chrome browser, widely recognized for its speed and efficiency in processing JavaScript. So, Node.js essentially transforms JavaScript into a general-purpose programming language. With Node.js, you can build a vast array of applications, from responsive web servers and real-time chat applications to simple command-line tools and even complex desktop applications. It frees JavaScript from the browser's sandbox, the heart of Node.js, non-blocking I/O, and the event loop. The secret sauce behind Node.js's efficiency and scalability lies in two interconnected concepts: non-blocking I/O and the event loop. Let's revisit our second, more efficient coffee shop analogy. In Node.js, when your application needs to perform an I/O operation, say, fetching a user's profile from a database, it doesn't wait around for the database to send the data back like a traditional system might. Instead, it simply initiates the request and tells the operating system, "Hey, fetch this data for me and notify me when it's ready." Then, critically, it immediately moves on to process other tasks or serve other users. This continuous activity while waiting for external operations is the essence of non-blocking I/O, but how does Node.js know when the data is ready amidst all this activity? This is where the event loop comes in. Imagine the event loop as Node.js's vigilant manager or a highly organized queue handler. It continuously monitors a sequence of events or tasks. When an I/O operation finishes, for example, the database finally returns the user's profile data. It generates an event and places a callback function, a designated piece of code designed to handle that specific response, into a special queue. The event loop then systematically picks up these completed callbacks from the queue and executes them when the main line of execution for your application logic is available. This sophisticated mechanism means that while Node.js itself largely operates on a single thread, meaning it processes your primary application logic one instruction at a time, it can effectively handle a huge number of concurrent operations. It achieves this by intelligently offloading I/O tasks to the operating system or other threads, and then processing their results asynchronously when they become available. It's like our smart barista, who can manage many drink orders without ever being idled, thanks to their efficient system of taking orders and then working on whatever is ready next. This design makes Node.js incredibly efficient for applications that involve many concurrent connections or frequent data interactions, minimizing waiting times and maximizing the system's ability to serve many users simultaneously. The rise of NPM, Node Package Manager. No discussion of Node.js would be complete without mentioning NPM, the Node Package Manager. When Node.js emerged, it wasn't just a runtime. It came bundled with a vibrant and rapidly growing package ecosystem. NPM is fundamentally two things. It's a command-line tool that helps you manage dependencies and run scripts for your Node.js projects, and it's a vast online registry of open-source software packages. Think of NPM as a global, collaborative library for JavaScript code. Need to send an email from your application? Someone has likely already built a robust package, a collection of reusable code modules for that, meticulously tested and ready to be installed directly from NPM. Want to connect to a specific type of database? There's probably an NPM package enabling that. This incredibly rich ecosystem allows developers to quickly integrate pre-built, community-vetted solutions into their projects, drastically accelerating development time and allowing them to build complex functionalities by standing on the shoulders of giants. Today, NPM hosts millions of packages, making it one of the largest software registries in the world, a testament to the power of open-source collaboration. Why choose Node.js? Key benefits. Businesses and developers worldwide have enthusiastically embraced Node.js for compelling and practical reasons. Unified language. For the first time in mainstream backend development, developers could use JavaScript for both the front end, what users see and interact with in their web browser, and the backend, the server-side logic and database interactions. This full-stack JavaScript approach minimizes context switching for developers, making teams more agile, efficient, and productive. It streamlines the entire development process. Exceptional performance and scalability. Thanks to its core design around non-blocking I/O and its event-driven architecture, Node.js excels at gracefully handling many concurrent connections with minimal overhead. This makes it an ideal choice for building highly responsive web services, real-time applications, and other systems that need to scale efficiently to serve a large number of users simultaneously. Vast and active ecosystem. The NPM registry provides immediate and easy access to a phenomenal number of pre-built modules, libraries, and tools. This significantly reduces the need to reinvent the wheel, allowing developers to build complex applications quickly and efficiently by leveraging existing, well-tested solutions. Boosted developer productivity. Node.js's streamlined development process, combined with its unified language stack and rich ecosystem, translates directly into faster development cycles. Developers can prototype ideas, build features, and deploy applications with remarkable speed. Strong community support. With millions of developers actively using Node.js, there's a large, vibrant, and continuously growing community. This means abundant online resources, forums, active open-source contributions, and readily available support, which is invaluable for learning and problem-solving. Where does Node.js shine? Common use cases. While Node.js is incredibly versatile, like any technology, it tends to be an exceptionally strong fit for certain types of applications. Real-time applications. Its unparalleled ability to handle a large number of simultaneous, persistent connections makes it perfect for applications requiring instant updates, such as chat platforms, live dashboards, online multiplayer gaming, and collaborative editing tools. APIs and microservices. Many modern companies leverage Node.js to build the backend application programming interfaces, APIs, that serve data and functionality to their web, mobile, and desktop applications. Its efficiency also makes it well-suited for building small, independent services, often referred to as microservices, which form a larger system. Data streaming. Node.js can efficiently process and stream data in chunks, rather than waiting for an entire file or dataset to load into memory. This is particularly useful for bandwidth-intensive applications like video streaming services, audio processing, or proxying requests for large file uploads. Serverless architectures. Node.js is one of the most popular choices for developing serverless functions, e.g., on platforms like Oz Lambda, Google Cloud Functions, or Azure Functions. Here, developers write discrete bits of code that run in response to specific events, without having to manage the underlying server infrastructure directly. Command line tools, CLIs. Many widely used developer tools and utilities, from project scaffolding tools to build process managers, are built using Node.js, showcasing its flexibility beyond just web servers. A brief glimpse ahead. While Node.js offers incredible advantages, like any powerful technology, it has its nuances and considerations. For instance, its single-threaded nature means that extremely heavy, CPU-intensive computations, like complex mathematical calculations, intensive data encryption-decryption, or large-scale image processing, can potentially block the event loop, impacting performance for other tasks. However, it's crucial to understand that there are well-established patterns and tools specifically designed to address such challenges, allowing Node.js to scale effectively even in these scenarios. We will delve into these solutions and other best practices in later chapters. The Node.js revolution truly changed the landscape of backend development, liberating JavaScript to run anywhere and ushering in an era of efficient, scalable, and elegantly real-time applications. As you embark on this exciting journey, you'll discover how its unique design principles make it an indispensable tool for building the robust backbone of modern digital experiences. In the next chapter, we'll dive deeper into the essential JavaScript foundations you'll need to master before you can confidently and effectively build with Node.js. Chapter 2. JavaScript's New Home. Essential Concepts for Node.js. In our previous chapter, we explored how Node.js liberates JavaScript from the confines of the web browser, transforming it into a versatile tool for building powerful server-side and desktop applications. But before we can truly harness the power of Node.js, we need to ensure our understanding of JavaScript itself is solid. Node.js is, after all, simply an environment for JavaScript. Think of it this way. To build a magnificent structure with a new, powerful set of tools, you first need to be proficient with the fundamental building material. In our case, that material is modern JavaScript. Even if you've dabbled with JavaScript in a web browser, Node.js development often requires a deeper grasp of certain concepts. It's no longer just about manipulating website elements. It's about structuring complex programs, handling data, and managing operations efficiently. Declaring your intentions, variables with let and const. At its most basic, programming involves storing and manipulating information. JavaScript handles this through variables. While older versions of JavaScript primarily use the var keyword for declaring variables, modern JavaScript, often referred to as ECMAScript 2015 or ES6 and beyond, introduced two much-preferred alternatives: let and const. Use let when you expect the value of a variable to change over time. Imagine a counter for the number of items in a shopping cart. This number will increase or decrease as items are added or removed. Let declares a variable whose value can be reassigned. Variables declared with let also have what's called block scope, meaning they only exist within the specific code block, like an if statement or a loop, where they are defined, which helps prevent unexpected behavior in larger programs. Const, short for constant. Const is used for values that should not change after they are initially assigned. Consider a variable holding the number, pi, or a fixed configuration setting like a database address. Once you assign a value to a const variable, you cannot reassign it later. This strictness can be surprisingly helpful for preventing accidental modifications and making your code more predictable. Like let, const also uses block scope. The general recommendation in modern JavaScript development, especially within Node.js applications, is to favor const by default. If you later discover that a variable's value truly needs to change, then you can switch to let. The var keyword is largely considered outdated for general use in new code due to some quirks in its scope behavior, but you might still encounter it in older code bases. The workhorses, functions, and their flexibility. Functions are the fundamental building blocks for organizing and reusing code. They allow you to encapsulate a set of instructions that perform a specific task, such as calculating a value, processing data, or interacting with a system. In JavaScript, functions are incredibly flexible. They are considered first-class citizens, which means you can treat them like any other value, much like you would a number or a piece of text. This unique property allows you to assign functions to variables. You can store a function in a const or let variable and then call it using that variable's name. Pass functions as arguments to other functions. This is a crucial concept for asynchronous programming, which we will explore in detail in the next chapter. Higher-order functions, which either take functions as arguments or return functions, are very common in JavaScript. Return functions from other functions. This enables powerful patterns like creating functions on the fly or providing configurable operations. Modern JavaScript also introduced arrow functions, a more concise way to write functions. They are particularly popular for shorter functions and for situations where the behavior of the this keyword, which we'll discuss next, needs to be more predictable. Arrow functions can often make your code cleaner and easier to read. Containers for information, objects and arrays. Beyond simple numbers and text, real-world applications deal with complex data. JavaScript provides two primary structures for organizing collections of data. Objects, best understood as collections of key-value pairs. Each key is a name, like name or age, and it points to a corresponding value, like Alice or 30. Objects are excellent for representing entities with distinct properties, such as a user profile with a name, email address, and ID, or a configuration file with various settings. The keys are like labels on different compartments in a box, and the values are what's stored inside each compartment. Arrays, these are ordered lists of values. Think of a grocery list. Milk is item 1, eggs are item 2, and bread is item 3. Each item has a specific position, starting from 0. Arrays are ideal when the order of items matters, or when you have a collection of similar items, such as a list of user IDs, a sequence of measurements, or a collection of blog posts. Both objects and arrays are highly dynamic. You can easily add, remove, or modify their contents after they've been created, making them very adaptable for handling changing data. Navigating context. The this keyword, one of the most frequently misunderstood aspects of JavaScript, especially for newcomers, is the this keyword. Its value isn't fixed. Instead, it largely depends on how a function is called, rather than where it's defined. Imagine this as a magical spotlight that shines on different objects depending on the context. When a function is called as a method of an object, e.g., user say hello, this usually refers to that object user in this case. The spotlight is on the specific object that owned the method. When a function is called normally, not as a method of an object, e.g., say hello, this might refer to the global object, like the window object in browsers or a special global object in Node.js, or be undefined in strict mode. The spotlight is just generally out in the open. Arrow functions handle this differently. They do not have their own this. Instead, they inherit this from the surrounding code where they were defined. This makes them very predictable and often preferred when you want to ensure this points to a specific object. Understanding this is vital for writing robust Node.js applications, especially when dealing with classes or event handlers where functions might be called from different contexts. The power of rememory, scope, and closures. Every time you write JavaScript code, your variables and functions exist within a scope. Think of scope as the visibility of your variables. A variable defined inside a function is only visible within that function. It's like a note passed around only within a specific room. Variables defined outside any function are generally global and visible everywhere, like a public announcement. Block scope, introduced with let and const, further refines this, making variables visible only within the curly braces, where they are declared. This helps prevent variables from clashing or being accidentally modified in unrelated parts of your program. One of JavaScript's most powerful features, directly related to scope, is closures. A closure occurs when a function remembers its surrounding environment, its lexical scope, even after that environment has completed execution. Imagine a private tutoring session. The tutor, your function, remembers specific notes and insights, the variables from its outer scope that were shared during their initial preparation. Long after the preparation time itself, the outer function's execution has ended. When the tutor then conducts the actual session, they can still access those private notes. Closures are fundamental to many advanced JavaScript patterns, including how asynchronous operations, like handling network requests or timers, maintain their context, and how private data can be created within objects. Building blueprints, prototypes, and classes. JavaScript is often described as a prototype-based language, meaning that objects inherit properties and methods from other objects. They're prototypes. This is different from traditional programming languages that use classes as blueprints for creating objects. However, recognizing that many developers are familiar with class-based object-oriented programming, modern JavaScript introduced the class keyword. This class syntax is largely syntactic sugar, a more convenient way to write code that internally still uses JavaScript's prototype inheritance model. Think of a class as a blueprint or a template for creating objects. If you're building an application that manages different types of users, administrators, regular users, guests, you might create a user class that defines common properties like name, email, and behaviors like login, logout. Then, you can easily create many user objects, each with its own specific data, based on that single blueprint. Using classes helps structure your code in a clear and organized way, making it easier to manage complex applications. Modern JavaScript goodies. Beyond the basics, modern JavaScript continuously evolves, adding new features that make code cleaner, more readable, and more efficient. Some notable additions you'll frequently use in Node.js include destructuring assignment, a concise way to extract values from arrays or properties from objects into distinct variables. Instead of repeatedly writing user.name and user email, you can extract name and email directly into their own variables. Template literals. These allow you to embed expressions and variables directly within string text enclosed by backticks. This makes constructing dynamic text, such as messages or HTML snippets, much simpler than traditional string concatenation. Default parameters. You can now define default values for function parameters, so if an argument is not provided when the function is called, it will use the predefined default instead. Spread and rest syntax. The three-dot syntax has dual purposes. The spread operator allows you to expand iterables, like arrays or strings, into individual elements. The rest parameter collects multiple function arguments into a single array. Both dramatically simplify handling collections of data. These features, while seemingly small, contribute significantly to writing more elegant and maintainable Node.js applications. The foundation for the future. This chapter has provided a whirlwind tour of essential JavaScript concepts crucial for your Node.js journey. Understanding let and const, the versatility of functions, the structure of objects and arrays, the often tricky this keyword, the power of closures, and the elegance of modern JavaScript features will serve as your bedrock. As we move forward, we'll see how these concepts are applied creatively within the Node.js ecosystem, particularly when dealing with the asynchronous nature that gives Node.js its impressive performance. In the next chapter, we'll demystify this asynchronous heartbeat, diving deep into callbacks, promises, and the increasingly popular async await syntax, which are all built on these very JavaScript fundamentals. Chapter 3, the asynchronous heartbeat, understanding callbacks, promises, and async await. In Chapter 1, we introduced the concept of Node.js's non-blocking I/O and the event loop, likening it to an efficient coffee shop where the barista never idles, always moving on to the next task while waiting for others to complete. Chapter 2 laid the groundwork of essential JavaScript concepts. Now, we're ready to dive into the very core of how Node.js achieves that efficiency. Through its unique approach to handling operations that take time, known as asynchronous programming. Most operations in a computer program happen incredibly fast. But some, particularly those involving input-output, such as reading a file from your hard drive, sending data over a network, or querying a database, can take a relatively long time. In a traditional, synchronous system, if your program asks to read a large file, it would simply pause, waiting for the entire file to be read before it could do anything else. This is the blocking behavior we discussed, like our first coffee shop barista waiting for a single espresso to finish before taking the next order. To avoid this paralysis, Node.js embraces an asynchronous model. This fundamentally means that when you ask Node.js to perform a time-consuming operation, it initiates the task but doesn't wait for it to finish. Instead, it gets a promise that the operation will complete eventually and immediately moves on to process other tasks. When the long-running operation finally finishes, Node.js is notified, and it can then execute the code that depends on that result. This is the non-blocking nature in action, and it's powered by three primary patterns: callbacks, promises, and async await. The original pattern, callbacks. The callback function is the most fundamental and original way JavaScript handled asynchronous operations. A callback function is simply a function that is passed as an argument to another function, and it is intended to be executed after the first function has completed a particular task. Imagine you're ordering a custom-made cake. You tell the baker your specifications and then provide your phone number. You don't stand there for hours watching them bake. You go home and do other things. When the cake is ready, the baker calls you back using the number you provided. That phone call and your subsequent action, picking up the cake, are the real-world equivalent of a callback. In Node.js, when you tell it to read a file, you'd provide it with a callback function. Node.js initiates the file read, moves on to other tasks, and once the file is fully read, it executes your callback function, typically passing the file's content or any errors that occurred. While simple for one-off tasks, managing multiple sequential asynchronous operations with callbacks can become complicated. If you need to read file A, then process its content, then use that processed data to fetch data B from a database, and then update user C based on data B, your code can quickly become deeply nested, resembling a pyramid or a sideways Christmas tree of curly braces. This infamous pattern is often referred to as callback hell or the pyramid of doom, making code hard to read, debug, and maintain. Enter promises, a better way to manage asynchronous operations. To address the complexities of deeply nested callbacks, the JavaScript community adopted promises. A promise is an object that represents the eventual completion or failure of an asynchronous operation and its resulting value. It's like a placeholder for a value that isn't known yet, but will be at some point in the future. Think of a promise as a delivery receipt you get when you order something online. When you place the order, you don't get the item immediately, but you get a receipt. This receipt, the promise, has a state: pending. The operation is ongoing. The item has been ordered but not yet shipped or delivered. Fulfilled or resolved. The operation completed successfully and you have the result. The item has been delivered. Rejected. The operation failed and you have an error. The item was lost in transit or was out of stock. Instead of passing a callback directly, with promises, you attach functions to the promise object using methods like then and catch. The then method is called when the promise is fulfilled, the operation succeeds. It receives the successful result. The catch method is called if the promise is rejected, the operation fails. It receives the error information. The real power of promises comes from their ability to be chained. Because then and catch methods themselves return new promises, you can link multiple asynchronous operations together in a much flatter, more readable sequence, avoiding the pyramid of doom. Each then block processes the result of the previous one, making the flow of data much clearer. This significantly improved the readability and maintainability of complex asynchronous code in Node.js. The modern solution, async await. While promises brought a significant improvement over callbacks, the language continued to evolve. The introduction of async await keywords provided an even more elegant and intuitive way to work with promises, making asynchronous code look and feel almost as if it were synchronous. It's essentially syntactic sugar built on top of promises, meaning it uses promises behind the scenes but provides a much cleaner syntax. Imagine you're an assembly line worker performing tasks one after another. If a task requires waiting for a part to arrive, you could stop everything, go home, and come back whenever the part arrived, like callbacks. Or you could get a commitment that the part will arrive and sign up for a notification, like promises. But with async await, it's like a magical pause button. You just press pause on your current task, and the moment the part you're waiting for arrives, you automatically resume right where you left off, without having to explicitly then your way back. Here's how it works. The async keyword is placed before a function declaration. This signals that the function will perform asynchronous operations and will always return a promise. The await keyword can only be used inside an async function. When placed before a promise, it pauses the execution of the async function until that promise settles, either fulfills or rejects. If the promise resolves, await returns its resolved value. If it rejects, await throws an error. This allows you to write asynchronous code that reads top to bottom, just like synchronous code, greatly improving readability. Error handling with async await also becomes more straightforward, moving from chained catch blocks to familiar try ... catch statements, making it easier to manage exceptions just as you would in synchronous code. Choosing your asynchronous tool. In modern Node.js development, async await is the preferred and most widely adopted method for handling asynchronous operations due to its superior readability and simplified error handling. Promises are still fundamental as async await builds upon them, and you'll encounter them frequently, especially when working with older code or third-party libraries. Callbacks, while less common for new asynchronous code, are still prevalent in Node.js's core modules, which we'll explore in the next chapter, and older libraries, so recognizing and understanding them remains important. Understanding callbacks, promises, and async await is paramount to mastering Node.js. It's not just about syntax, it's about grasping the fundamental event-driven, non-blocking nature that makes Node.js so powerful and efficient. Armed with this knowledge, you are now ready to explore the built-in capabilities of Node.js that leverage these asynchronous patterns to interact with your computer's file system, networks, and more. Our next chapter will delve into these essential tools, Node.js's core modules. Chapter 4, Under the Hood, exploring Node.js core modules. In the earlier chapters, we talked about Node.js as a powerful runtime environment for JavaScript and delved into the crucial concept of asynchronous programming. Now, it's time to look under the hood and understand the built-in functionalities that empower Node.js applications to perform essential tasks like reading files, handling network requests, and interacting with the operating system. These are what we call core modules. Think of Node.js as a well-equipped workshop. While you can bring in specialized tools from the outside, which we'll explore when we discuss NPM and packages, the workshop itself comes pre-stocked with a fundamental set of high-quality, reliable tools designed for common tasks. These are the core modules. They are integral to the Node.js installation, meaning you don't need to download or install them separately. They are always available, ready for use, directly accessible within any Node.js application. When you want to use a core module, you simply tell Node.js by requiring it, almost like asking a librarian for a specific book from their permanent collection. For example, to gain access to the tools for manipulating your computer's file system, you would just declare your intent to use the File System module. Let's explore some of the most frequently used and fundamental core modules that you'll encounter in nearly every Node.js project. The FS module, your file system navigator. Perhaps one of the most common tasks for any server-side application is interacting with files. Whether it's reading configuration settings, logging events, or storing user-uploaded content, the Node.js FS module, short for File System, provides all the necessary functionalities. The FS module acts like a highly capable librarian for your computer's storage. It allows your Node.js application to read files, open a book file, and read its contents. You can read entire files into memory or read them piece by piece, which is useful for very large files. Write files. Create a new book or update an existing one. You can write text, binary data, or anything else you need. Create or delete directories. Build new shelves, directories, or remove old ones. Check file status. See if a book file exists, check its size, or find out when it was last modified. Crucially, nearly all operations within the FS module are available in both synchronous and asynchronous versions. Remembering our discussion on non-blocking I/O, Node.js strongly encourages the use of the asynchronous versions. For instance, if you're reading a large file, the asynchronous version allows your application to start the reading process and immediately move on to serving other users. Once the file is fully read, your specified callback, function, or promise receives the data, allowing you to process it without ever stopping the main flow of your program. The synchronous versions, on the other hand, would halt your program until the file operation is complete, potentially freezing your application for other users. The HTTP module. Building your web server. The internet runs on HTTP, the Hypertext Transfer Protocol. If you want your Node.js application to respond to web browser requests, build APIs, or serve web pages, the HTTP module is your starting point. It provides the core functionality for creating web servers and making HTTP requests. Using the HTTP module, you can create a server. Imagine setting up a restaurant. The HTTP module allows you to open your restaurant's doors, listen on a specific network port, and await customers' incoming web requests. Handle requests. When a customer web browser makes an order, sends an HTTP request, your server can interpret what they're asking for. For example, they might be requesting a specific web page or submitting data from a form. Send responses. After processing the request, your server prepares a response, like a dish from the kitchen, and sends it back to the customer, the web browser. This response might be an HTML web page, a JSON data structure, an image, or simply a confirmation message. While the HTTP module provides the raw building blocks, handling complex routing, middleware, and request parsing can become quite verbose. This is why, in practical applications, developers often use web frameworks like Express.js, which we'll cover in a later chapter. Express.js largely builds upon the HTTP module, providing a much higher level, more convenient, and more opinionated way to construct web applications, saving you from having to manage every tiny detail of the HTTP conversation yourself. Nevertheless, understanding the HTTP module is fundamental to grasping how web applications fundamentally operate in Node.js. The path module, navigating directories with ease. Different operating systems, like Windows, macOS, and Linux, use different conventions for writing file paths. Windows often uses backslashes, to separate folders, while macOS and Linux use forward slashes. Directly concatenating path strings in your code can lead to issues when your application is deployed on a different operating system. The path module is designed to solve this problem. It acts as a universal navigator for your computer's file system, providing utilities for working with file and directory paths in a way that is consistent across all operating systems. With the path module, you can join path segments, combine folder names and file names into a correct, full path regardless of the operating system. Extract parts of a path. Get just the file name, the file extension, or the directory name from a full path string. Resolve absolute paths. Turn a relative path, like current folder/myfile.txt, into a full path that starts from the root of your hard drive. Using the path module prevents subtle bugs and ensures your application behaves reliably whether it's running on a Windows server, a Linux virtual machine, or a macOS development environment. The OS module, your operating system's info hub. Sometimes your application needs to know information about the environment it's running in. How much free memory does the computer have? What's the computer's hostname? Is it a 64-bit system? The OS module offers a range of methods for interacting with the operating system on which Node.js is running. It can provide details such as the current operating system platform, e.g., Win32, Darwin, Linux, the system's total and free memory, information about the computer's CPUs, how many cores, models, etc., the system's uptime, how long it has been running, the network interfaces available on the machine. This information can be crucial for monitoring your application, making environment-specific decisions, or gathering diagnostic data. The Events module, building your own notification system. Node.js is inherently event-driven, and the Events module is at the heart of this paradigm. It provides the event emitter class, which allows you to create and manage custom events within your application. Think of it like setting up a notification system. You define certain events that can happen, e.g., user logged in, data saved, file processed. Other parts of your application can then listen for these events. When an event occurs, all the functions that are listening for that specific event are automatically executed. This pattern is fundamental because it allows different parts of your application to communicate with each other without being tightly dependent. The part that emits an event doesn't need to know who is listening or what they will do with the information. It just announces that something has happened. This promotes a modular and flexible architecture. Many core Node.js modules, like HTTP and FS, internally use event emitter to signal when requests arrive or file operations complete, demonstrating its widespread importance. The util module, handy utilities. As its name suggests, the util module provides a collection of small but useful utility functions that can help with various programming tasks. One particularly notable utility is Permissify. Recalling our discussion from Chapter 3, Permissify is a helper function that takes a traditional Node.js function that uses the callback pattern and automatically wraps it, returning a new version of that function that works with promises. This is incredibly useful for modernizing older codebases or integrating libraries that might not yet have native promise support, allowing you to use the cleaner async await syntax even with callback-based functions. The power of foundation. These core modules form the sturdy foundation upon which all Node.js applications are built. They provide low-level access to critical system resources and enable the core capabilities that make Node.js so versatile for server-side development. While you'll often interact with these functionalities through higher-level libraries and frameworks, understanding them is key to truly grasping how Node.js operates and efficiently manages resources. In the next chapter, we'll move beyond the built-in tools and explore the vast world of external packages. We'll dive into Node Package Manager, NPM, learning how to leverage millions of open-source software modules to accelerate your development and build even more complex and powerful applications. Chapter 5, The Package Powerhouse, Navigating NPM and Project Management. In the previous chapter, we explored the essential Node.js core modules, which are like the fundamental tools pre-packaged in your workshop. Now, we're going to open the doors to a much larger world, the vast ecosystem of third-party modules and libraries, managed primarily through the Node Package Manager, or NPM. Imagine the Node.js core modules as the basic hammer, screwdriver, and saw in your toolkit. They're essential, but sometimes you need a specialized power drill, a laser level, or a specific type of wrench that isn't included. That's where external packages come in. Node.js's strength lies not just in its runtime, but also in its unparalleled ability to leverage millions of pre-built, reusable code packages created and shared by a global community of developers. This open-source collection means you rarely have to reinvent the wheel, allowing you to build complex functionalities quickly and efficiently. What is NPM? More than just a command. As we briefly touched upon in Chapter 1, NPM serves two primary functions. The NPM registry. This is a gigantic, public online database that hosts millions of open-source packages. Think of it as a massive digital marketplace or a public library where developers upload their reusable code for others to discover and use. The NPM command line interface, CLI. This is the tool you install on your computer. It usually comes bundled with Node.js that allows you to interact with the NPM registry. It enables you to search for packages, download them, install them into your projects, manage their versions, and even publish your own packages. Together, the NPM registry and CLI form an incredibly powerful system that fosters collaboration and significantly accelerates development within the Node.js ecosystem. Starting a new Node.js project, NPM init. Every Node.js project typically begins with a special file called package.json. This file is the heart of your project's configuration and metadata. It's like the master blueprint for your entire construction project. It contains project information, its name, version, description, author, license, and so on. Scripts, custom commands that you can run using NPM, such as commands to start your application, run tests, or build your code. Dependencies, a list of all the third-party packages your project relies on to function. This is crucial for project management. Dev dependencies, a list of packages that are only needed during development, e.g., testing frameworks, code formatters, but not when the application is actually running in production. To create this package.json file, you use the npm init command. When you run npm init, it will interactively prompt you for basic information about your project, guiding you through the creation of this essential file. After answering a few questions, npm generates the package.json file for you, which you can then modify manually as needed. Installing packages. npm install. Once your package.json is set up, the real power of npm comes into play. Installing external packages. Let's say you want to use the popular Lodash package, a utility library that provides helpful functions for common programming tasks. You would open your terminal in your project's directory and type npm install Lodash. When you run this command, npm downloads Lodash. The npm CLI connects to the npm registry, finds the Lodash package, and downloads its code. Node modules folder is created. npm places the downloaded Lodash code, and any packages Lodash itself depends on, into a new directory inside your project called node_modules/. This folder contains all the installed dependencies for your project. You should generally not manually modify files within Node modules, and you typically don't include this folder when sharing your code on version control systems like Git. Package.json is updated. Crucially, npm adds Lodash to the dependencies section of your package.json file, along with the version number it installed. This records that your project relies on Lodash. Package.lock.json is created updated. Alongside package.json, another file called package.lock.json is automatically generated or updated. This file acts as a precise record of the exact versions of every single package and subpackage installed in your Node modules folder. Its purpose is to ensure that when anyone else, or you, at a later date, runs npm install in your project, they get the identical set of dependencies, guaranteeing consistent builds across different environments. If you don't specify a package name, just run npm install. npm will look at your package.json file and install all of its listed dependencies and dev dependencies into the Node modules folder and create update package.lock.json. This is incredibly useful when you clone an existing Node.js project. You just run npm install, and all necessary external code is set up for you. To install packages that are only needed for development, like testing frameworks, you use the savedev flag or its shorthand D. npm install mocha savedev, or npm install mocha-d. This will add mocha to your dev dependencies section in package.json. Understanding package versions and semver. Managing package versions is vital to avoid unexpected breaking changes. NPM and the wider Node.js community adhere to a standard known as semantic versioning, SEMVer. SEMVer uses a three-part version number, major-minor patch. Patch, incremented for backward-compatible bug fixes, e.g. 1.0.0 to 1.0.1. Minor, incremented for backward-compatible new features, e.g. 1.0.0 to 1.1.0. Major, incremented for backward-incompatible changes, breaks existing code, e.g. 1.0.0 to 2.0.0. When NPM adds a dependency to your package.json, it typically uses a caret symbol before the version number, e.g. Ladesh 4.17.21. The caret tells NPM, install the latest minor or patch version that is compatible with this major version. For example, 4.17.21 means NPM can install 4.18.0 or 4.17.22, but not 5.0.0. This balance allows for bug fixes and new features while generally preventing breaking changes. The package.lock.json file then precisely locks down the exact version installed, ensuring consistency across environments. Running scripts, npm run. The scripts section in package.json allows you to define custom commands to automate common tasks in your project. For example, you might have a script for starting your web server, another for running tests, and yet another for compiling your code. In your package.json, a script, start node index.js, test mocha, dev nodeman server.js. To run these scripts, you use the npm run command followed by the script name, npm run start, npm run test, npm run dev. For commonly named scripts like start, test, install, and restart, you can omit the run keyword, npm start or npm test. This feature makes it incredibly easy to standardize project workflows and abstracts away complex command line arguments. Global versus local installation. When you run npm install package name, the package is typically installed locally to your project's Node modules folder. This is the recommended approach for most packages, as it isolates dependencies to each project, preventing version conflicts between different applications on your system. Sometimes, however, you need command line tools that should be accessible from anywhere on your system, not just within a specific project. For these, you can install packages globally using the G flag. npm install nodeman g. Nodeman is a popular tool that automatically restarts your Node.js application when it detects file changes, which is very useful during development. Installing it globally means you can then simply type nodeman in any project directory to use it. Other useful npm commands. npm uninstall package name removes a package from your Node modules and updates package.json and package.lock.json. npm update package name updates a package to the latest version allowed by your package.json, respecting SEMVer rules. npm audit scans your project's dependencies for known security vulnerabilities and suggests fixes. This is a crucial command for maintaining secure applications. npm outdated shows which of your installed packages are outdated compared to the latest versions available in the registry. Package.json and Node modules, best practices. Commit package.json and package.lock.json. Always add these files to your version control system, like Git. They are essential for others to be able to replicate your project's exact dependency setup. Do not commit Node modules. This folder can be very large, containing thousands of files, and it can be easily regenerated by running npm install. Add node modules / to your gitignore file to prevent accidentally committing it. Keep dependencies minimal. Only install packages you truly need. Too many dependencies can increase your application's size, complexity, and potential for security vulnerabilities. Regularly audit your dependencies. Use npm audit to check for security issues, and consider using tools that automatically scan your dependencies for vulnerabilities. Navigating the npm ecosystem is an indispensable skill for any Node.js developer. It transforms Node.js from a powerful runtime into an extraordinary platform for rapid application development. By understanding package.json, npm install, and the principles of dependency management, you gain access to a world of pre-built solutions. In our next chapter, we'll put these tools into action as we begin to build our first web server using Node.js and the popular Express.js framework. Chapter 6. Your first server. Building web applications with Node.js and Express.js. In Chapter 4, we briefly touched upon the Node.js HTTP module, explaining how it provides the fundamental building blocks for creating web servers and handling HTTP requests. While powerful, using the raw HTTP module for anything beyond the simplest, most basic web application can quickly become cumbersome. You'd find yourself manually parsing request URLs, differentiating between HTTP methods like GET and POST, and meticulously constructing responses for every single path. This is a bit like building a house entirely from scratch, hammering together every single piece of wood and mixing every batch of mortar by hand. This is where web frameworks come into play. A web framework provides a structured set of tools, libraries, and conventions that streamline the process of building web applications. It handles much of the repetitive boilerplate code, allowing you to focus on your application's unique logic. In the Node.js ecosystem, the most popular and widely adopted web framework is Express.js. Why Express.js? Express.js is often described as a fast, unopinionated, minimalist web framework for Node.js. Fast, it's built for performance, leveraging Node.js's asynchronous nature. Unopinionated, unlike some larger frameworks, Express doesn't force you into a particular architectural pattern or database choice. It gives you a lot of freedom, which can be liberating, but also means you'll need to make design decisions yourself. Minimalist. It provides a lean core set of features for routing and middleware, but it doesn't come with everything, including the kitchen sink. You add other libraries and tools as needed, making your application as small or as large as it needs to be. Express simplifies common web development tasks, making it much easier to define how your server should respond to different web addresses and requests. Setting up your first Express application. Before we write our first server, we need to install Express.js into our project. Just like any other external package we discussed in Chapter 5, we use the Node Package Manager, NPM. Assuming you've already created a project directory and initialized it with npm init, you would simply type into your terminal, npm install express. This command downloads the Express.js library and adds it to your project's Node modules folder, and lists it as a dependency in your package.json file. Now, let's conceptualize the basic structure of an Express application. Bring in Express. The very first step in almost any Express application is to import the library into your JavaScript file. This makes all of Express's functionalities available to your code. Create an application instance. You then create an instance of the Express application. This instance, often named app, becomes the central object for configuring your server, defining routes, applying middleware, and listening for incoming requests. Define routes. This is where you tell your server what to do when a specific web address, URL path, is accessed with a particular HTTP method, like opening a page with GET or submitting a form with POST. For example, you might define a route that handles requests to your website's homepage, another for an About Us page, and another for handling user logins. Start the server. Finally, you tell your Express application to start listening for incoming web requests on a specified network port. This is like opening your restaurant's doors for business on a particular street number. Understanding routes. The paths of your web application. In the context of a web server, a route defines how your application responds to a specific HTTP request at a particular URL path. Each route usually corresponds to a unique combination of an HTTP method and a URL path. Let's imagine some common scenarios. GET requests. These are used to retrieve data. When you type www.yourwebsite.com into your browser, you're making a GET request for the homepage. If you navigate to www.yourwebsite.com/products, you're making a GET request to retrieve a list of products. Post requests. These are used to send data to the server, often for creation or submission. When you fill out a contact form and click Submit, your browser typically sends a post request with your form data. Put patch requests, used for updating existing data. Delete requests, used for removing data. In Express.js, you define a route using the app instance, followed by the HTTP method, and then the path string. For example, to handle a GET request to the route path, you would conceptually write something like appget/handler function. The handler function is where you put the logic for what happens when that route is accessed. This function always receives two important objects: request object, often named rec. This object contains all the information about the incoming client request. This includes things like the URL path, e.g., products 123, any data sent by the client, e.g., form submissions, JSON data, information about the client's browser or operating system, parameters extracted from the URL, e.g., 123 from products 123. Response object, often named raise. This object is what you use to send a response back to the client. With the response object, you can send plain text messages, send HTML pages, send JSON data, very common for APIs. Set HTTP status codes, e.g., 200 for success, 404 for not found, 500 for server error. Redirect the client to another URL. For example, a simple route handler for a homepage might use the response object to send back a friendly "Hello, world" message. A route for products might fetch data about products and then use the response object to send that data formatted as JSON. The power of middleware. Intercepting and processing requests. One of the most powerful and flexible features of Express.js is middleware. Imagine an assembly line for processing incoming requests. As a request arrives at your server, it doesn't go directly to its final destination, the route handler. Instead, it can pass through a series of middleware functions, each performing a specific task. Each middleware function has the ability to execute any code, make changes to the request and response objects, end the request-response cycle, e.g., send a response back to the client and stop further processing, call the next middleware function in the stack. Think of middleware as security guards, log keepers, and data processors stationed at various checkpoints. For instance, a logging middleware might record every incoming request's URL and the time it arrived. An authentication middleware might check if a user is logged in before allowing them to access certain pages. If not, it could redirect them to a login page. A body parsing middleware, like Express's built-in Express.json, can automatically take incoming JSON data from a client and make it easily accessible in your request object. A static file serving middleware can handle requests for public files like CSS stylesheets, JavaScript files for the browser, and images, automatically sending them back to the client without needing a specific route handler for each file. You apply middleware using the app.use method. If you pass a path to app.use, the middleware only applies to requests that begin with that path. If you don't provide a path, the middleware applies to every incoming request, making it ideal for global tasks like logging or parsing. The order in which you declare your middleware matters, as they are executed sequentially. Serving static files. Many web applications need to serve static assets like HTML files, CSS stylesheets, client-side JavaScript, and images. Express provides an easy way to do this using a built-in middleware function. You simply tell Express which folder contains your public static files, and it will automatically serve them when requested. This means you don't need to manually create routes for every single image or CSS file, putting it all together, a simple web server. With these concepts, you can already envision building a functional web server with Express.js. Set up Express. Define a route for your homepage GET that sends back a simple HTML page or a welcome message. Perhaps define another route, GetAbout, for an About Us page. Add a middleware to serve static files from a public folder, so your HTML can link to CSS and images. Finally, tell your application to listen on a specific port, like 3000, so you can access it from your web browser at http localhost:3000. This foundational setup forms the backbone of almost any Express.js application, from simple websites to complex application programming interfaces, often referred to as APIs. In the coming chapters, we will build upon this foundation. exploring how to connect our Node.js and Express application to databases, design robust APIs, and handle the intricacies of real-world application development. Chapter 7, Data Persistence, Connecting Node.js to Databases. In our journey so far, we've learned how Node.js allows us to build powerful web applications and API servers using Express.js. We can handle requests, send responses, and even serve static files. However, there's a crucial piece missing. What happens to our data when the server restarts? If a user signs up for an account, where does that account information go? If a new product is added to an online store, how does it stay there permanently? The simple answer is that variables and data stored purely in a running Node.js application's memory are temporary. When the application stops or restarts, that information is lost forever. To overcome this, we need data persistence, the ability for data to outlive the process that created it. This is where databases come into play. Imagine your server as a highly efficient, short-term memory system. It can process information quickly, but it forgets everything once it's powered down. A database, on the other hand, is like a massive, highly organized library or filing cabinet. It's designed to reliably store, retrieve, update, and delete vast amounts of information for the long term, even if the power goes out. What is a database? At its core, a database is an organized collection of information, structured so that it can be easily accessed, managed, and updated. It's not just a collection of files. It's managed by a specialized software application called a Database Management System, DBMS. The DBMS handles all the intricate details of storing data safely on disk, managing concurrent access from multiple users, and ensuring data integrity. There are many types of databases, each with its own strengths and weaknesses. The two broadest categories you'll encounter are relational databases, SQL, and non-relational databases, NoSQL. The choice between them depends heavily on the nature of your data, the type of application you're building, and your scalability requirements. Relational databases, SQL. The structured approach. Relational databases have been the standard for decades, and for good reason. They are based on the relational model, where data is organized into tables, often called relations. Each table has a predefined structure, consisting of columns, which define the type of data, and rows, which contain the actual data. These tables can be linked together using common fields, establishing relationships between different pieces of information. Think of a relational database as a collection of meticulously organized spreadsheets, where each spreadsheet represents a table, and columns are clearly defined with specific data types: text, numbers, dates. These spreadsheets can even be linked together. For instance, a customer's spreadsheet linked to an orders spreadsheet by a common customer ID column. Key characteristics of relational databases: structured schema. Data fits into predefined tables with strict column definitions. If you want to add a new type of information, you usually have to alter the table structure. SQL, structured query language. This is the universal language used to interact with relational databases. For creating tables, inserting data, querying for specific information, updating records, and deleting them. ACID properties. Relational databases emphasize ACID guarantees, atomicity, all or nothing operations. If one part of a transaction fails, the entire transaction is rolled back. Consistency. A transaction brings the database from one valid state to another. Isolation. Concurrent transactions don't interfere with each other. Durability. Once a transaction is committed, it remains permanently. These properties make them incredibly reliable for applications where data integrity and consistency are paramount, like financial systems or inventory management. Popular examples of relational databases include PostgreSQL, MySQL, SQLite, a lightweight, file-based database often used for local storage or small applications, and Microsoft SQL Server. You would typically choose a relational database when your data has a clear, predictable structure, when relationships between data points are important, and when you require strong data consistency guarantees. Non-relational databases, NoSQL, the flexible approach. The term NoSQL stands for not only SQL, reflecting a broader category of databases that deviate from the traditional relational model. They emerged to address the limitations of relational databases when dealing with massive datasets, highly flexible or unstructured data, and the need for extreme scalability and performance in certain scenarios. Instead of tables and rows, NoSQL databases employ various data models. Document databases store data in flexible, semi-structured formats, typically JSON-like documents. Each document can have a different structure, making them highly adaptable to changing data requirements. MongoDB is a prominent example. These are great for content management systems, user profiles, or e-commerce product catalogs where items might have varied attributes. Key-value stores, the simplest form, storing data as simple key-value pairs like a large dictionary. Redis and Amazon DynamoDB are examples. Excellent for caching, session management, or storing user preferences where lightning-fast reads and writes are crucial. Graph databases, designed for data where relationships between entities are as important as the entities themselves. Data is stored as nodes, entities, and edges relationships. Neo4j is a popular choice, ideal for social networks, recommendation engines, or fraud detection. Column family stores store data in columns rather than rows, good for handling large analytical workloads or massive amounts of data with sparse attributes. Apache Cassandra is a well-known example. Key characteristics of NoSQL databases: flexible schema, often schemaless or with a very flexible schema, allowing for rapid iteration and evolution of your data model without complex migrations. Horizontal scalability. Many NoSQL databases are designed to scale horizontally by distributing data across many servers, making them well-suited for handling very high traffic. Base properties. Many NoSQL databases prioritize base over ACID. Basically available, the system will always be available for queries. Soft state. The system state might change over time, even without input. Eventually consistent. Data will eventually propagate through the system, and all queries will return the same data, but not necessarily immediately. This paradigm shift makes them excellent for real-time applications, big data analytics, or situations where immediate consistency can be relaxed for greater availability and performance. You might choose a NoSQL database when you need extreme scalability, when your data structure is constantly evolving, or when you're dealing with very large volumes of rapidly changing data that doesn't fit neatly into rows and columns. Connecting Node.js to databases, the bridge. Node.js applications typically don't communicate with databases directly using low-level network protocols. Instead, they rely on libraries that act as convenient bridges. These libraries fall into two main categories: database drivers. These are low-level client libraries specific to a particular database. They handle the direct communication, connection pooling, and error handling. For example, if you're using PostgreSQL, you might use the PG driver. If you're using MongoDB, you'd use the MongoDB driver. These drivers allow you to send raw database commands, like SQL queries for relational databases or JSON-based queries for NoSQL document databases, and receive the raw results. Object Relational Mappers, ORMs/Object Document Mappers, ODMs. These are higher-level abstraction layers built on top of database drivers. ORMs are used with relational databases, while ODMs are for document databases. Their primary purpose is to allow you to interact with your database using familiar JavaScript objects and code, rather than having to write all your database queries in SQL or low-level database-specific syntax. How ORMs/ODMs work. They essentially map your JavaScript objects to database records. For instance, a JavaScript user object with id, name, and email properties can be mapped to a user's table in a relational database or a user document in a NoSQL database. You can then perform operations like saving a user, finding users by their name, or updating a user's email address by calling methods on your JavaScript objects. And the ORM/ODM translates these commands into the appropriate database queries behind the scenes. Benefits: ORMs/ODMs significantly boost developer productivity, reduce boilerplate code, make database interactions more readable, and can sometimes offer a degree of database independence. making it easier to switch database types if needed. Examples: for relational databases in Node.js, popular ORMs include Sequelize, Prisma, and TypeORM. For MongoDB, the most widely used ODM is Mongoose. Regardless of whether you use a low-level driver or a high-level ORM ODM, it's crucial to remember that database operations in Node.js are almost always asynchronous. When your Node.js application sends a query to the database, it doesn't wait for the response to come back. Instead, it continues processing other requests. When the database eventually sends back the results or an error, Node.js uses callbacks, promises, or async await, as discussed in Chapter 3, to execute the code that handles that response. This non-blocking behavior is essential for maintaining the high concurrency and scalability that Node.js is known for. By connecting your Node.js application to a database, you unlock the ability to build dynamic, data-driven applications that can store and manage user accounts, product catalogs, order histories, and much more. This persistent storage capability transforms your server from a fleeting computational tool into a robust, living data guardian. With our data now safely stored, the next logical step is to decide how we want to retrieve and manipulate this data for our client applications. This leads us directly to the concept of APIs, which we will explore in the next chapter. Chapter 8, Crafting Clean APIs, Principles of REST-TFL Design. In the previous chapter, we connected our Node.js application to a database, providing it with the essential capability to persistently store and retrieve data. Now that we have a robust data backend, the next logical step is to expose this data and its associated functionalities to other applications in a structured, consistent, and understandable way. This is where APIs, or application programming interfaces, come into play. What is an API? The language of software. At its simplest, an API defines a set of rules and protocols by which different software components or applications can communicate with each other. Imagine a restaurant. The menu is the API. You don't go into the kitchen and directly tell the chef how to cook your meal. That's the internal logic of the application. Instead, you use the menu, the API, to order a specific dish, make a request, and the waiter brings it to your table. The API provides a response. The menu defines what you can order and what to expect in return. In the context of web applications, when we talk about APIs, we are usually referring to web APIs. These allow a client application, like a web browser, a mobile app, or another server, to communicate with a server application over the internet, exchanging data and triggering operations. For example, when you use a mobile banking app, it's constantly making API calls to your bank servers to fetch your balance, transfer funds, or view statements. Why are APIs so important today? APIs are the backbone of modern interconnected applications. Separation of concerns. They allow you to build your front end, the user interface, and backend, server logic and database, independently. A single backend API can serve data to a web application, an iOS app, an Android app, and even smart home devices. Modularity and reusability. Developers can build specialized services, e.g., an authentication service, a payment service, and expose them via APIs, allowing other parts of the system or even external partners to use those functionalities. Integration. APIs are how different services talk to each other. Think of how many apps integrate with Google Maps, Twitter, or PayPal, all through their respective APIs. Scalability. By separating the front end from the back end, each can be scaled independently based on their specific needs. While there are various styles of web APIs, one has dominated the landscape for many years. REST-TFL APIs. Introduction to REST-TFL design. REST stands for Representational State Transfer. It's not a protocol or a strict standard, but rather a set of architectural principles or guidelines for designing networked applications. It was introduced by computer scientist Roy Fielding in 2000. REST-TFL APIs aim to be simple, flexible, and efficient, leveraging the existing standards of the web, particularly HTTP. The core idea behind REST is to treat everything as a resource. A resource is simply any piece of information or functionality that can be identified by a unique address, typically a URL. For instance, in an e-commerce application, a product, a user, or an order are all examples of resources. Key principles of RESTful API design: resources and resource URIs. Every significant entity in your system should be considered a resource. Resources are identified by unique uniform resource identifiers, URIs, which are commonly just URLs. Naming convention: resource URLs should use nouns, be plural, and reflect a hierarchical structure. For example, instead of get users or create product, you would use users for a collection of users and products for a collection of products. To refer to a specific user, you'd use /users/ID, e.g., users123. For more specific relationships, you might have users 123 orders to get orders for user 123. Avoid verbs in your URLs as the HTTP methods convey the action. Statelessness: this is a fundamental principle of REST. Every request from a client to the server must contain all the information necessary for the server to understand and process that request. The server should not rely on any previously stored information, session data, or client context from the client to fulfill the current request. Imagine talking to a new person for every interaction. You tell them your name and what you need in every sentence. This simplifies server design, improves scalability, as any server can handle any request, and makes the API more reliable. Client-server architecture: there's a clear separation between the client, e.g., a web browser or mobile app requesting data, and the server, your Node.js application providing the data. This separation allows each to evolve independently. Uniform interface: this is the most critical principle for the simplicity of the system. It means that there's a standardized way to interact with resources regardless of the specific resource. This is achieved primarily through HTTP methods, verbs. Standard HTTP methods are used to perform actions on resources. Resource identification: using URIs for unique resource identification. Self-descriptive messages: each message contains enough information to describe how to process it. Hypermedia as the engine of application state, HATOS. This principle suggests that responses should include links to related resources, allowing clients to discover available actions without hard-coding URLs. While a core part of formal REST, it's often the least strictly adhered to in practical RESTful API implementations. HTTP methods, verbs, and their actions. HTTP methods are the verbs that describe the action you want to perform on a resource, identified by a URL. Get retrieves a representation of a resource or a collection of resources. It should be safe, no side effects on the server, and idempotent, making the same GET request multiple times has the same outcome. Example: get all users. Get users. Example: get a specific user. Get users 123. Post creates a new resource. The data for the new resource is sent in the request body. Example: create a new user. Post users with user data in the body. Put updates an existing resource with the provided data. It implies a complete replacement of the resource. If the resource doesn't exist, PUT might create it, though post is generally preferred for creation. PUT is idempotent. Example: update user 123. PUT users 123 with full user data in the body. Patch partially updates an existing resource. Only the fields that need to be changed are sent in the request body. Patch is not necessarily idempotent. Example: change user 123's email. Patch users 123 with only email data in the body. Delete removes a specific resource. Delete is idempotent. Example: delete user 123. Delete users 123. Status codes, communicating success and failure. The server communicates the outcome of an API request using HTTP status codes. These 3-digit numbers provide essential feedback to the client. 2XX, success, indicates that the client's request was successfully received, understood, and accepted. 200 OK, general success. 201 created. Resource successfully created, typically after a post request. 204 no content. Request processed successfully, but there's no content to return, often for delete requests. 4XX client errors. means there was a problem with the client's request. 400 bad request. The server cannot process the request due to malformed syntax. 401 unauthorized. Authentication is required and has failed or needs to be provided. 403 forbidden. The client doesn't have permission to access the resource. 404 not found. The requested resource could not be found on the server. 405 method not allowed. The HTTP method used is not supported for the requested resource. 5xx server errors indicates that the server failed to fulfill a valid request. 500 internal server error. A generic error message for an unexpected condition that prevented the server from fulfilling the request. Data representation. JSON is king. While REST-TFL APIs can technically use various data formats, JSON, JavaScript object notation, has become the de facto standard for exchanging data between client and server. JSON is lightweight, easy for humans to read and write, and easy for machines to parse and generate. It maps perfectly to JavaScript objects and arrays, making it incredibly convenient to work within Node.js applications. Designing a REST-TFL API with Node.js and Express.js. In practice, building a REST-TFL API with Node.js and Express.js involves defining your resources. Identify the key data entities your application will manage, e.g., users, products, orders. Mapping resources to URLs. Based on the plural noun convention, e.g., /API/users/API/products. Implementing HTTP methods for CRUD operations. To get all users, you'll define and express root app-get /API/users. Inside this root, you'd query your database to retrieve all user records and send them back as JSON. To get a single user, app-get /API/users/ID. Here, id is a root parameter that Express parses for you, and you'd use it to query your database for that specific user. To create a user, app-post /API/users. You would expect the user's data in the request body, which expresses Express.json. Middleware can parse, validate it, save it to the database, and respond with a 201 created status code and the newly created user's data. To update a user, app-put /API/users/ID or app-patch /API/users/D. To delete a user, app.delete /API/users/D. Handling status codes and errors. Always return appropriate HTTP status codes based on the outcome of the operation. If something goes wrong, return an error status code, e.g., 400, 404, 500, and an informative JSON error message. Benefits of REST-TFL APIs. Scalability. The stateless nature makes it easy to scale by adding more servers. Flexibility. Clients and servers can be developed and updated independently. Interoperability. Standard HTTP methods and JSON make it easy for diverse clients, web, mobile, IoT, and other servers to consume the API. Simplicity. It directly leverages the well-understood architecture of the web. While REST has been the dominant design pattern, it's worth noting that other API styles, like GraphQL, which allows clients to request exactly the data they need, reducing overfetching, and gRPC, emphasizing high performance and efficient data transfer, have gained popularity for specific use cases. However, REST remains incredibly pervasive and is an excellent starting point for any API developer. By adhering to these REST-TFL principles, you can craft well-structured, predictable, and easy-to-consume APIs that form the foundation for powerful and interconnected applications. In the next chapter, we'll shift our focus from building features to ensuring the robustness of our applications by learning how to properly handle errors and debug issues, which is critical for any API or web server. Chapter 9, Handling the Unexpected, Error Management and Debugging in Node.js. No matter how carefully you write your code, things will eventually go wrong. Networks might fail, databases could become temporarily unavailable, users might enter invalid data, or a subtle logical flaw you missed could surface under specific conditions. In the world of software development, these things that go wrong are errors, and how gracefully your application handles them can differentiate a robust, reliable system from one prone to crashing and frustrating users. Effective error management is paramount for any production-ready Node.js application. It's not just about preventing crashes, it's about maintaining data integrity, providing meaningful feedback to users, and ensuring the application remains available. Hand in hand with error management is debugging, the process of identifying, locating, and fixing defects or bugs in your code. Just like a detective needs tools and techniques to solve a mystery, a developer needs specific approaches to find the root cause of an unexpected behavior. The nature of errors in Node.js. Errors in Node.js generally fall into two broad categories. Operational errors. These are problems that occur during normal operation, often due to external factors or invalid input. They are predictable and should be handled programmatically. Examples include a file not being found when your application tries to read it, a database connection timing out or returning an error, a network request failing because the remote server is down, invalid data provided by a user, e.g., trying to save a negative age, exceeding a rate limit when calling an external API. These errors do not indicate a bug in your code, but rather an expected, albeit undesirable, outcome that your application should anticipate and manage gracefully. Programmer errors. These are actual bugs or defects in your code. They are mistakes made by the developer during the coding process. Examples include a typo in a variable name, attempting to call a method on an undefined object, an infinite loop, incorrect logic that leads to an unexpected result. These errors typically require changes to the code itself to resolve. While robust error handling can sometimes catch these, the ultimate solution is to fix the underlying bug. Strategies for error management. Node.js, with its asynchronous nature, has distinct patterns for handling errors. 1. The asynchronous error-first callback pattern. Historically, Node.js core modules heavily relied on the error-first callback pattern for asynchronous operations. When using callbacks, the first argument to the callback function is conventionally reserved for an error object. If an error occurs, it's passed as the first argument. Otherwise, it's null or undefined, and the subsequent arguments contain the successful result. For example, when reading a file, the callback function receives error and data arguments. If error is present, it means something went wrong, e.g., file not found. You must check for this error and handle it before attempting to use the data. Neglecting to check for and handle the error will lead to unexpected behavior later or potentially crashed applications. 2. Promises and the catch method. As we discussed in Chapter 3, promises introduced a much cleaner way to handle asynchronous errors. A promise can either resolve, succeed, or reject, fail. If a promise rejects, the error is propagated down the chain until a catch method handles it. Using catch at the end of a promise chain is similar to a try ... catch block for synchronous code, designed to capture any errors that occur at any point in the asynchronous flow. This makes error handling more centralized and readable compared to individual if error checks in nested callbacks. 3. Async await and try ... catch. The async await syntax, built on top of promises, further simplifies asynchronous error handling by allowing you to use traditional try ... catch blocks. Within an async function, any await operation that results in a rejected promise will immediately throw an error that can be caught by a surrounding try ... catch block. This pattern makes asynchronous code look and feel remarkably similar to synchronous code, making error handling intuitive and familiar for developers coming from other languages. It has become the preferred method for asynchronous error handling in modern Node.js applications. 4. Global error handlers, a last resort. While try ... catch, promises, and async await handle errors within specific parts of your code, sometimes an error goes completely unhandled. Node.js provides global event listeners for such scenarios. Process on, uncaught exception. This event fires when a synchronous error occurs that is not caught by any try ... catch block. If this happens, your Node.js process is in an undefined state. It's crucial to understand that you should not attempt to continue normal application operation after an uncaught exception. The best practice is to perform graceful shutdown procedures, e.g., log the error, close database connections, and then exit the process, so that a process manager can restart the application cleanly. Process on unhandled rejection. This event fires when a promise is rejected, but there is no catch handler to deal with that rejection. Similar to uncaught exception, you should log the error and perform a graceful shutdown. These global handlers are safety nets. Their presence means that a serious bug likely exists in your code that needs to be fixed. They prevent your application from merely crashing silently, offering a chance to log critical information before gracefully shutting down. Best practices for robust error management. Handle errors promptly. Don't ignore errors. If an asynchronous operation can fail, always provide a way to catch and respond to that failure. Centralized error handling. In larger applications, especially Express.js APIs, it's common to have a single, centralized error handling middleware. This middleware catches all errors throughout your application and sends a consistent, user-friendly error response, usually JSON, to the client, while internally logging detailed error information. Distinguish operational from programmer errors. When logging, differentiate between these two types. Operational errors might be logged as warnings or info, while programmer errors should usually be critical or error-level logs, triggering alerts for developers. Provide user-friendly errors. For external-facing APIs, as discussed in Chapter 8, don't expose raw stack traces or internal server details in your response. Instead, provide generic but informative messages, e.g., invalid input, internal server error, and appropriate HTTP status codes, e.g., 400 bad request, 500 internal server error. Log everything important. Use a robust logging library, like Winston or Pinot, available via NPM to capture detailed information about errors, including stack traces, request details, and debugging information. Log events should be immutable and contain enough context to reproduce the issue. Avoid empty catch blocks. An empty catch block silently swallows errors, making debugging extremely difficult. At a minimum, log the error even if you can't immediately fix it. Graceful shutdown. For critical unhandled errors, plan for your application to shut down cleanly. This might involve flushing logs, pushing metrics, or closing connections to ensure data integrity before the process exits. The art of debugging. Even with the best error handling, bugs will inevitably creep into your code. Debugging is the process of finding and fixing them. 1. The print statement, debugger, console log. The simplest and most common debugging technique is to strategically place console log statements throughout your code to inspect variable values, confirm code execution paths, and understand flow. While effective for simple issues, it can become cumbersome for complex problems or large code bases, often requiring you to add and remove many lines of code. 2. The Node.js inspector, built-in debugger. Node.js comes with a powerful built-in debugger that you can access. When you start your Node.js application with the Node inspect flag, it opens a debugging port. You can then connect to this port using a Chrome DevTools client. Simply open Chrome//inspect in your Chrome browser or a dedicated IDE. This allows you to set breakpoints. Pause your code execution at specific lines. It's like hitting the pause button on a movie right at the moment you want to examine. Step through code. Execute your code line by line, allowing you to observe exactly what happens at each step. Inspect variables. See the current values of all variables in scope, local, global, module level. Modify variables. In some debuggers, you can even change variable values on the fly to test different scenarios. Call stack. See the sequence of function calls that led to the current execution point. This interactive debugging experience is far more efficient than console log for complex issues, as it gives you granular control over the execution flow and visibility into the application state. 3. Leveraging IDEs for debugging. Modern integrated development environments. IDEs, like Visual Studio Code, WebStorm, or others, provide excellent integrated debugging experiences for Node.js. They abstract away the command line details, allowing you to set breakpoints directly in your code editor simply by clicking in the margin. You can then launch your application in debug mode directly from the IDE, stepping through code, watching variables, and setting conditional breakpoints, which only pause execution when a certain condition is met with a visual interface. This is often the most user-friendly and powerful way to debug Node.js applications. 4. When to consider profilers. For performance-related issues, where your application is slow or consuming too many resources, debuggers might not be enough. Profilers are specialized tools that help you understand where your application spends its time, e.g., which functions are consuming the most CPU or memory. Node.js can generate CPU profiles, and tools like Chrome DevTools can visualize these, helping you pinpoint performance bottlenecks. This is a more advanced technique, but invaluable when optimizing critical paths in your application. Mastering error management and debugging is a continuous journey. As your Node.js applications grow in complexity, these skills become increasingly vital for building reliable, maintainable, and high-quality software that can effectively handle the diverse challenges of real-world operations. In the next chapter, we'll shift our focus to another critical aspect of software quality, ensuring correctness and reliability through automated testing. Chapter 10, Ensuring Quality. Introduction to Testing Node.js Applications. Imagine you're an architect designing a magnificent skyscraper. You wouldn't just draw up the plans, hand them over to the construction crew, and hope for the best without any checks. Instead, you'd meticulously test the strength of the materials, verify the stability of the foundation, check the integrity of each pillar and beam, and finally, inspect the entire structure to ensure it can withstand the elements. In software development, this verification process is called testing. Just like with a skyscraper, building software without adequate testing is a recipe for disaster. Bugs, performance issues, and security vulnerabilities can creep into your code, leading to frustrated users, costly downtime, and damage to your reputation. For Node.js applications, which often power critical backend services and APIs, ensuring quality through effective testing is not just a good practice. It's essential for building reliable, maintainable, and scalable systems. Why test your code? Testing provides several crucial benefits. Confidence. It gives you and your team confidence that your application works as expected. When you make changes or add new features, tests can quickly tell you if you've accidentally broken existing functionality, a common problem known as regressions. Reliability. By catching bugs early, before they reach users, testing helps deliver a more stable and dependable product. Maintainability. Well-tested code is often easier to understand and refactor. Tests act as executable documentation, illustrating how different parts of your system are supposed to behave. Faster development. While it might seem counterintuitive, writing tests can actually speed up development in the long run. Debugging complex issues in production is far more time-consuming and expensive than fixing them during development. Better design. The act of writing tests often forces developers to think more carefully about the design of their code, leading to more modular, loosely coupled, and testable components. Types of testing. Not all tests are created equal. Different types of tests operate at different levels of granularity and serve different purposes. One-unit tests. Focus. Unit tests are the smallest, most granular form of testing. They focus on testing the individual, isolated units of your code. A unit is typically the smallest testable piece of code, such as a single function, a specific module, or a method within a class. Isolation. The key principle of unit testing is isolation. When testing a unit, you want to ensure it works correctly on its own, without external dependencies causing issues. This often involves mocking or stubbing any external components, like database calls, network requests, or file system operations, that the unit might interact with. Mocking means creating a fake version of a dependency that you control, allowing you to simulate specific behaviors or return predefined values. Analogy. Think of unit tests as meticulously inspecting each individual brick, screw, or small component of our skyscraper example. You're making sure each piece is perfectly formed and functions as intended, independent of how it fits into the larger structure. Benefits. Unit tests are generally very fast to run, making them ideal for frequent execution during development. When a unit test fails, It typically pinpoints the exact function or line of code that contains the bug, making it easy to identify and fix. 2. Integration tests. Focus. Integration tests verify that different units or modules of your application work correctly together. They focus beyond individual components to ensure that the interfaces and interactions between multiple parts of your system function as expected. Analogy. After testing individual bricks, integration tests would be like checking if the bricks connect properly to form a strong wall section, or if different wall sections connect to form a room. You're testing the connections and collaborations. Examples. An integration test might involve testing if your Express.js API endpoint correctly interacts with your database to save a user, or if one internal service correctly calls another. Unlike unit tests, they might involve actual database connections or file system reads, though often using a dedicated test database to avoid polluting production data. Benefits. Integration tests catch bugs that arise from incorrect assumptions about how components interact. They provide more confidence in the system's larger segments. 3. End-to-end, E2E, tests. Focus. End-to-end tests simulate a complete, real-world user flow through the entire system, from start to finish. They mimic how a user would interact with your application, typically involving the front end, if applicable, the backend API, and the database. Analogy. For our skyscraper, an E2E test would be like performing a full safety walkthrough, checking that elevators work, water flows from taps, doors open, and the entire building experience is seamless for an occupant. For a web application, it might involve automating a browser to click buttons, input text, and verify results on the screen. Benefits. E2E tests provide the highest level of confidence that your critical user journeys are functioning correctly. They catch issues that might be missed by lower-level tests, such as configuration errors or problems only apparent when the entire system is running. Drawbacks. E2E tests are typically the slowest to run, the most complex to set up, and can be brittle, easily broken by minor UI or API changes. They are best reserved for critical path scenarios. Common testing tools and frameworks in Node.js. The Node.js ecosystem offers a rich set of tools to support testing. Test runners. These are utilities that execute your tests, provide an interface for running specific tests, and aggregate test results. Jest, a very popular all-in-one testing framework, particularly prevalent in the JavaScript community. It includes a test runner, a powerful assertion library, and built-in mocking capabilities. It's often chosen for its ease of setup and comprehensive feature set. Mocha, a highly flexible and feature-rich test framework. While it provides the structure to write tests, it often pairs with other libraries for specific functionalities, like assertion or mocking. Assertion libraries. These libraries provide functions that allow you to express what you expect the outcome of your code to be. They are used to compare actual results with expected results. Chai, a popular assertion library that works well with Mocha. It provides a wide range of expressive assertion styles. Jest has its own built-in, powerful assertion methods that are typically used with Jest. Mocking stubbing libraries. When performing unit tests, you often need to isolate the code being tested from its dependencies. These libraries allow you to create fake versions of functions or modules that your code interacts with, letting you control their behavior during the test. Synonjs, a powerful standalone library for creating spies, stubs, and mocks, often used in conjunction with Mocha and Chai. Jest's built-in mocking functionality is very capable and widely used within the Jest framework. HTTP testing libraries. When testing Express.js APIs, integration tests, you need a way to simulate HTTP requests to your server without actually spinning up a full web server and using a tool like Postman. Superdist, an excellent library that simplifies testing HTTP endpoints. It allows you to make virtual HTTP requests to your Express app and then make assertions on the response status, headers, and body. Writing good tests, key principles. Regardless of the tools you choose, adhering to certain principles will help you write effective and maintainable tests. Arrange Act Assert, AAA pattern. A common and highly recommended structure for organizing your tests. Arrange, set up the test environment. This includes creating any necessary test data, initializing objects, or configuring mocks. Act. Execute the code that you are actually testing. This is typically a function call or an HTTP request. Assert. Verify the outcome. This involves making assertions about the return value, the state of objects, or the side effects that occurred, e.g., if a function was called a certain number of times. Isolation and independence. Each test should be able to run independently of others and in any order. They should not rely on the state left over from a previous test. This typically means cleaning up data or resetting mocks after each test run. Fast execution. Tests should run quickly, especially unit tests. This encourages developers to run them frequently, getting immediate feedback on their code changes. Readability and maintainability. Tests are a form of documentation. They should be easy to read and understand, clearly describing what aspect of the code is being tested and what the expected behavior is. Use descriptive test names. Test edge cases and error paths. Don't just test the happy path, successful scenarios. It's equally important to test what happens when invalid input is provided, when external services fail, or when other unexpected situations arise. This ties directly into the error management concepts we discussed in the previous chapter. From development to deployment, the role of continuous integration. Tests are most effective when they are run regularly. This is where continuous integration, CI, comes in. CI is a development practice where developers frequently integrate their code changes into a central repository. Every time a change is pushed, an automated system, a CI server, automatically builds the application and runs all the tests. If any tests fail, the team is immediately notified, allowing them to address the issue quickly before it escalates. This practice ensures that the codebase remains stable and functional, providing a robust safety net as new features are added and code evolves. Conclusion. Testing might seem like an extra step that slows down initial development, but it is a critical investment in your application's long-term health and your team's productivity. By embracing unit, integration, and end-to-end testing, and leveraging the powerful tools available in the Node.js ecosystem, you can build software with confidence, deliver higher quality products, and navigate changes with greater ease. It transforms the act of coding from a hopeful venture into a precise, verifiable engineering process. Next, we'll delve into securing your applications, ensuring that all the hard work you've put into building and testing your code is protected from malicious intent. Chapter 11, Securing Your Applications, Essential Best Practices. You've worked hard to build a robust and functional Node.js application. You've structured your code, managed your data, and ensured its quality through testing. Now, imagine putting all that effort into building a beautiful house, complete with all the modern amenities, but forgetting to install locks on the doors and windows. This is analogous to deploying an application without considering its security. In today's interconnected digital world, security is not an afterthought. It must be an integral part of your application's design and development from day one. Malicious actors are constantly looking for vulnerabilities to exploit, steal data, disrupt services, or gain unauthorized access. A single security breach can lead to severe financial losses, reputational damage, legal consequences, and a complete loss of user trust. For Node.js applications, which often handle sensitive data and critical backend operations, strong security practices are non-negotiable. This chapter will discuss essential security principles and common vulnerabilities, and provide best practices to harden your Node.js applications and protect them against potential threats. Understanding the landscape. Common vulnerabilities. Before we can protect our applications, we need to understand the typical ways they can be attacked. While the landscape of threats is constantly evolving, some common categories of vulnerabilities consistently appear. Understanding these will help us implement appropriate defenses. Injection attacks. This is a broad category where an attacker supplies untrusted input to a program that is then processed as part of a command or query. SQL injection. If you're building a Node.js application that interacts with a relational database, as discussed in Chapter 7, and you directly embed user-supplied input into raw SQL queries, An attacker could manipulate that input to execute arbitrary database commands. They might gain access to sensitive data, modify records, or even delete entire tables. NoSQL injection. Similar attacks can occur in NoSQL databases if user input is not properly handled when constructing queries or commands. Command injection. If your application ever executes shell commands based on user input, it could be vulnerable to arbitrary command execution on the server. Defense. The primary defense is never to trust user input. Always use prepared statements or object relational mappers, ORMs, with relational databases, and use equivalent safe methods for NoSQL databases and shell commands. These techniques separate the code from the data, preventing malicious input from being interpreted as executable commands. Cross-site scripting, XSS. This vulnerability allows attackers to inject malicious client-side scripts, often JavaScript, into web pages viewed by other users. When a user's browser executes the malicious script, it might steal cookies, session tokens, or other sensitive information, or even deface websites. Defense. Always sanitize and escape all user-supplied data before rendering it in the browser. This means converting characters that could be interpreted as code like and into their harmless HTML entities. Various NPM packages exist to help with this. Cross-site request forgery, CSRF. CSRF attacks trick authenticated users into unknowingly submitting a malicious request to a web application they are logged into. For example, an attacker might embed a hidden form on a malicious website that, when loaded, automatically makes a request to your application, e.g., to transfer money or change account settings, using the victim's authenticated session. Defense. Implement CSRF tokens. This involves generating a unique, unguessable token for each user session and embedding it in forms or HTTP headers. The server verifies this token with every state-changing request, like post, PUT, delete. If the token is missing or incorrect, the request is rejected. Broken authentication and session management. These refer to weaknesses in how user identities are verified and how sessions are managed, leading to compromised accounts. This includes weak passwords, default credentials, or insecure password storage, exposing sensitive session IDs in URLs, lack of session expiration or invalidation. Defense. Strong password hashing. Never store passwords in plain text. Always hash them using a strong, slow hashing algorithm like bcrypt. This makes it computationally expensive for attackers to crack passwords even if they gain access to your database. Secure session IDs. Generate long, random, unpredictable session IDs. Store them in HTTP-only cookies, which JavaScript cannot access, reducing XSS impact, and ensure they are transmitted over HTTPS. Implement aggressive session timeouts and invalidate sessions upon logout or password changes. Sensitive data exposure. Many applications fail to adequately protect sensitive data, both in transit and at rest. This can include personally identifiable information, PII, financial data, or authentication credentials. Defense. Use HTTPS everywhere. Always encrypt all communication between clients and your server using HTTPS, SSL TLS. This prevents eavesdropping and tampering. Encrypt data at rest. If highly sensitive data is stored in the database, consider encrypting it before storage. Environment variables. Never hardcode sensitive information, like API keys, database credentials, secret keys, directly into your code. Use environment variables, which we touched upon during project management in Chapter 5, or dedicated secrets management services. Insufficient logging and monitoring. Without proper logging and monitoring, it's impossible to detect, investigate, or recover from security incidents effectively. Defense. Record key security events, failed logins, access to sensitive resources, configuration changes with sufficient detail. Implement an alerting system that notifies you of suspicious activity. Essential security practices for Node.js applications. Beyond mitigating common vulnerabilities, there are overarching best practices you should adopt. Input-output validation and sanitization. This is your first and last line of defense. Validate all input. Treat all input from users, external APIs, and even internal services as untrusted. Validate its type, format, length, and range. Use robust validation libraries to enforce strict rules about what constitutes valid data. Sanitize all output. Before displaying any user-generated content back to the client, sanitize it to prevent XSS. Secure your dependencies, NPM audit. Malicious code can be injected into legitimate open-source packages. Regularly run NPM audit to check for known vulnerabilities in your project's dependencies. Keep your dependencies updated to receive security patches. Be cautious when adding new, less popular packages. Assess their reputation and maintenance status. Implement HTTPS, SSL, TLS. As mentioned, all traffic to and from your application should be encrypted. This protects against man-in-the-middle attacks and ensures data confidentiality and integrity. Robust authentication and authorization. Authentication. Verify who the user is. Use strong password policies, complexity requirements, minimum length, discourage common passwords. Authorization. Determine what an authenticated user is allowed to do. Implement role-based access control, RBAC, or attribute-based access control, ABAC, to enforce permissions. Always verify permissions on the server side, never solely rely on client-side checks. Rate limiting. Protect your application from brute force attacks, e.g., guessing passwords, and denial of service attempts by limiting the number of requests a user or IP address can make within a certain timeframe. Many Express.js middleware packages can help with this. Security headers. Configure your server to send appropriate HTTP security headers that instruct browsers on how to behave, enhancing client-side security. Examples include strict transport security, HSDS, forces browsers to use HTTPS. X-content type options prevents MIME sniffing. X-frame options prevents clickjacking attacks embedding your site in an iframe. Content security policy, CSP, mitigates XSS by whitelisting sources for content. Error handling revisited. As discussed in Chapter 9, generic error messages are crucial. Never leak sensitive information, database errors, or full-stack traces to the client in production environments. Log them internally for debugging, but present a generic error to the user. Principle of least privilege. Grant users, processes, and systems only the minimum level of access required to perform their intended function. For example, your database user for the application should not have administrative privileges. Regular security audits and updates. Stay informed about new vulnerabilities and security best practices through security feeds and communities. Regularly review your code for security flaws. Consider static application security testing, SAST, tools that analyze your code for known patterns of vulnerabilities. Keep Node.js itself updated to benefit from security patches. The human element. Ultimately, security is also about people. Educate your development team on secure coding practices. Foster a culture where security is everyone's responsibility, not just a single security expert. Nobody wants to be the headline of a data breach. By adopting a proactive and layered approach to security, you can significantly reduce your application's risk profile and build systems that are not just functional, but also trustworthy and resilient. With your application now functional, tested, and secured, the final frontier is to make it available to the world. Our next and final chapter will guide you through the process of deploying your Node.js application, taking it from your local machine to a live, accessible environment. Chapter 12, From Localhost to the World, Deploying Node.js Applications. You've planned, you've coded, you've debugged, and you've tested. Your Node.js application, be it a powerful API server, a real-time chat application, or a sophisticated web service, runs flawlessly on your local machine. But an application running only on your computer is like a magnificent painting hidden away in a private studio. Nobody else can see or use it. The final, exhilarating step in the development process is deployment. Taking your perfectly crafted application from your local development environment and making it available to the world, accessible to users across the internet. This is where your Node.js masterpiece moves from localhost to its permanent public address. It's akin to moving from a detailed prototype built in your garage to a mass-produced product that needs to run continuously, reliably, and at scale in a bustling factory. Deployment introduces an entirely new set of considerations compared to local development. On your machine, you might manually start your application, and if it crashes, you restart it. In production, your application needs to be robust, secure, performant, and resilient enough to handle real-world traffic, potential errors, and continuous operation without constant manual intervention. Key considerations for production deployment. Before diving into specific deployment methods, there are fundamental concepts you must understand and implement for a production-ready Node.js application. Environment variables. As discussed in Chapter 11, never hardcode sensitive information or environment-specific configurations directly into your code. Database connection strings, API keys, third-party service credentials, and even the application's operating port should be stored as environment variables. This allows you to easily switch between different configurations for development, testing, and production environments without changing the code itself. Your deployment platform will provide mechanisms to set these variables securely. Process management. Node.js by default operates within a single process. If that process crashes due to an unhandled error, which, despite your best error handling from Chapter 9, can still occur, your application stops. For continuous operation, you need a process manager. A process manager monitors your Node.js application, ensures it's always running, and automatically restarts it if it crashes. It can also manage multiple instances of your application for better performance and resilience. A popular example in the Node.js world is PM2, reverse proxies. Directly exposing a Node.js application to the internet is generally not recommended. Instead, applications are often placed behind a reverse proxy. Think of a reverse proxy as a traffic cop and a security guard at the entrance of your factory. It acts as the intermediary between clients, web browsers, and your Node.js application. Load balancing. If you have multiple instances of your Node.js app, the reverse proxy can distribute incoming traffic evenly among them. SSL termination. It can handle encrypting and decrypting data using HTTPS, offloading this CPU-intensive task from your Node.js application. Static file serving. It can serve static assets, like HTML, CSS, JavaScript images directly, which is faster and more efficient as Node.js can focus on dynamic logic. Security. It can filter malicious requests and provide an additional layer of security. Common reverse proxies include Nginx, pronounced Nginx, and Caddy. Scaling. As your application grows and more users interact with it, you'll need it to handle increased load. Horizontal scaling. This involves running multiple instances of your application, often across different servers, and using a load balancer, often part of a reverse proxy, to distribute requests among them. Node.js, with its non-blocking I/O and stateless nature, is well suited for horizontal scaling. Vertical scaling. This involves upgrading your existing server with more CPU, memory, or storage. This has limits, however, and horizontal scaling is generally preferred for high availability and fault tolerance. Deployment methodologies and platforms. The approach you take to deploy your Node.js application often depends on your budget, team's expertise, and the specific needs of your application. 1. Platform as a Service PaaS. Concept. This is the quickest and easiest way to get your application online. With PaaS, you focus solely on your code. The platform handles all the underlying infrastructure servers, operating systems, networking, databases, and scaling. You simply push your code, and the platform deploys and runs it. Pros: extremely easy to use, very fast deployment times, minimal operational overhead, built-in scaling and monitoring. Cons: less control over the underlying infrastructure, potential vendor lock-in, can become more expensive at very large scales compared to self-managed infrastructure. Examples: Heroku, Render, Google App Engine, AWS Elastic Beanstalk. How it works simplified. You link your code repository, e.g. GitHub, specify your Node.js version and start command, and the PaaS platform takes care of the rest. 2. Infrastructure as a service, IaaS, virtual private servers, VPS. Concept: with IaaS, you rent virtual machines, virtual servers, and have complete control over them from the operating system up. You handle everything: installing Node.js, setting up a process manager like PM2, configuring a reverse proxy like Nginx, and managing security updates. Pros: full control over the server environment, highly customizable, potentially more cost-effective for dedicated resources once you have the expertise. Cons: requires significant server administration knowledge, Linux command line, networking, security, more manual setup, higher operational overhead. Examples: AWS EC2, DigitalOcean Droplets, Linode, Google Compute Engine, Azure Virtual Machines. How it works simplified. You provision a virtual server, connect to it remotely via SSH, install Node.js, set up PM2 to keep your app running, configure Nginx to route traffic to your Node.js app, and set up your domain's DNS records to point to the server's IP address. 3. Containerization, Docker and Kubernetes. Concept: Docker allows you to package your application and all its dependencies, Node.js runtime, libraries, environment settings, into a single, isolated unit called a container. This container runs consistently across any environment, from your local machine to your production server. Kubernetes then acts as an orchestrator for managing and scaling many such containers across a cluster of machines. Pros: ensures consistent environments, solving "it works on my machine" problems, highly portable, excellent for scalability and microservices architectures, as discussed in Chapter 1, efficient resource utilization. Cons: steeper learning curve, requires understanding Docker files and container orchestration concepts, additional tooling. How it works simplified. You define a Docker file that describes how to build your Node.js application into an image. Then you build that image, push it to a container registry, and finally deploy the container to a Docker host or a Kubernetes cluster. Provided by cloud providers like AWS EKS, Google Kubernetes Engine, Azure AKS, or self-hosted. 4. Serverless functions. Concept: instead of deploying an entire server, you deploy individual functions that execute in response to specific events, e.g., an HTTP request, a file upload, a database change. You only pay for the compute time consumed when your function is actually running. The cloud provider automatically manages the underlying infrastructure and scales your functions based on demand. Node.js is an excellent choice for serverless functions due to its fast startup times. Pros: auto-scaling, virtually no server management, highly cost-effective for intermittent workloads, high availability. Cons: can introduce cold starts, a slight delay for the first request after an idle period, vendor lock-in, limited execution duration, less suitable for long-running processes or applications with persistent open connections. Examples: AWS Lambda, Google Cloud Functions, Azure Functions. How it works simplified. You write your Node.js function, configure it with a trigger, e.g., an API gateway endpoint for HTTP requests, and deploy it. The cloud platform handles invoking your function whenever the trigger event occurs, preparing your application for production. Regardless of your chosen deployment method, certain steps are critical to optimize your Node.js application for a production environment. Optimize for performance, minimize heavy computations in your main event loop. Streamline database queries, ensure you're not loading unnecessary modules. Robust logging and monitoring. Beyond console log, use a production-grade logging library, like Winston or Pinot, that can send logs to a centralized log management system, e.g., Elastic Stack CloudWatch logs. Set up monitoring tools to track application performance, errors, and resource usage, allowing you to proactively identify and resolve issues. Strict error handling. Revisit Chapter 9. All asynchronous operations must have proper error handling. Implement middleware for catching unhandled errors and returning appropriate, but non-revealing, responses to clients. Security measures. Review and implement all the security best practices from Chapter 11. Ensure all sensitive configurations are pulled from environment variables, not hard-coded. Build process. If your application uses TypeScript, Babel, or other tools that transform your source code. Ensure you have a robust build process to compile your code into production-ready JavaScript. Minimize and bundle your client-side assets, CSS, JavaScript. Continuous integration and continuous deployment, CI/CD. For efficient and reliable deployments, automate your build, test, and deployment process. A CI/CD pipeline, using tools like GitHub Actions, GitLab CI/CD, or Jenkins, automatically builds your application, runs all tests, as discussed in Chapter 10, and then deploys it to your chosen platform, minimizing manual errors and speeding up release cycles. The journey continues. Deploying your Node.js application to the world is a significant milestone, transforming your code into a living service. It marks the transition from development to an ongoing cycle of operation, monitoring, debugging, and continuous improvement. As your application gains users and evolves, you'll iterate on your deployment strategy, scale your infrastructure, and refine your processes to ensure it remains a reliable and performant cornerstone of the digital landscape. With the knowledge gained throughout this book, you are now equipped to confidently build, operate, and maintain modern applications powered by Node.js.